Sometimes visualizing these 3D equations can be pretty difficult, so we're going to try to do that in this video. Let's say we want to calculate the area between curves. And so we'll have one like this, goes from A to B. We'll have one curve here at the top and another one just below it. And we're trying to figure out this area that's right in between. So, let's use a simple formula. We just want to integrate from A to B, and we're going to try to subtract these two formulas. So, f of x minus g of x dx. All right, there we go. It's a simple formula there for that one. Now let's take another case. Let's say it was going to be perhaps crossing. So here's one curve and here's another curve. It's going to be crossing at this point C right here. And we want to try to figure out this area. Here's point A, here's point B. Well, really what we're going to need is we're going to have to split this up into two different integrals. So we're actually going to calculate this integral on this side and then this integral on this side. And sometimes for, different types of curve situations, there are going to be different types of setups you might need. Here's just a couple examples. And it's not going to be the end all be all here, but here's a couple. So in this particular case, we're going to go from A, and here's point C right here. We got A, and we're going to go to C. And that's only going to be for f of x. That's the blue one right here. F of x dx, just like we did on this side, but this time we're going to add a completely separate integral from C to B. And that's for gx over here, dx. And that'll nicely give us a couple of areas here for these two scenarios. All right, now for the disk, the washer method, and the slicing method. Let's kind of combine that all into one, because it's all the same stuff. The disk, washer, slices. We kind of want to think of this as if we were counting a stack of CDs. So here's our stack of CDs. It's actually going to be stacked along the x-axis over here. From A to B. And again, we're counting a stack of CDs right here. All right, so let's say sometimes we might even want a little hole cut out of here. So that's a hole right there. It's going to create an area that we're going to need to delete from the center. And here's our equation we can use. We got V equals the integral. If we're going to try to calculate this volume here, first of all, we're going to want to figure out if it's a cylinder, the volume of the cylinder. We can say, okay, look, we want to figure out the area of this particular CD, right? The surface area, and then multiply it by the height. Area times the height, and you'll get the volume, right? Okay, so how do we get the area of this? It's just going to be pi r squared, right? Pi r squared for the area of the circle. So we can put that over here. Forget about the integral for now, but pi r, and I'll make it like this because we're going to have a big R on the top right here. It's going to be r squared, and then a smaller r that we're going to subtract, so minus r squared. Okay, great. And remember this integral that we had? It's going to go from A to B, of course. A to B, that's the height, right? It's the same thing as integrating along this particular thing is the same thing as the height. That little integral right there, so that's dx. Okay, great. And then when is the best way to use this method? Well, if you're going to be integrating along the axis of rotation, so let's say we're integrating along this axis right here, A to B, and the axis that we are rotating around is the same axis. Same thing on this way. Sometimes you might want to be doing it for the y instead of x. You might rotate it across the y-axis like this. But if it's the same axis of rotation, so your integration is the same, integrate x, and you're going to rotate on x. That makes sense right there. In this particular case, r is equal to f of x. Sometimes r might equal, the y version of f of x. So, but yeah, so that's going to be how you'd use the disk and Washington method. And the slicing method's all the same thing. Let's compare that to the shell method over here. The shell method, which is going to be more like thickness of a roll of tape. Thickness of rolling tape. And so before we were dealing with an area, but in this particular case, we're going to have to sort of deal with just a circumference because we don't have an area. If we just have one single strip of tape along that's wrapped around that thing, it's just going to be empty inside of here. There's no area. It's just going to be a circumference on the top. So we'll start with that. If we want to try to figure out the volume, we're going to try to calculate the circumference. Circumference would be 2 pi r, right? In this case, our r is going to be r in blue, and then we can try to figure out the height, right? If we're going to try to figure out the area of this, it's the circumference there, and then there is going to be an area across here, but there wasn't any here. So now we got the surface area. We could integrate it across the thickness. All right, let's say there was like a little gap in the middle as well. Let's not forget the gap. Put that right here. And we're going to integrate that across a thickness. So however thick that tape is, that's the distance you're going to integrate, the thickness of the tape. So A to B is your thickness. All right, and it may not start at the origin. It may start at the 0, but it may not. Anyway, so it's going to be from A to B, A to B in blue here, and dx over here. All right, and that's going to be our volume of the shell, is kind of the thickness of this roll of tape here. In this particular case, h is equal to f of x, and r is equal to x. All right, but of course, just like before, you might be able to use this in two different scenarios. Let's say if you've got integrating, of course, is the opposite. So you're now integrating across the x-axis here, but you're going to be rotating across the y-axis. Okay? Or if you were integrating across the y-axis, like this, maybe it would look something like that. Then you would actually be rotating across the x-axis like this. So integrate on the x, and you're going to rotate on the y. All right. So this is the shell method. You can see how it just compares to the disk wash method. That was more like counting a stack of CDs, counting it one by one, the slices, and this is more like you got this thing of tape, and you want to figure out the thickness there. That's what you're integrating and figure out that volume. It's kind of weird. Now let's try to figure out the arc length of let's see, like of a line. So arc length, and just draw it out here real quick. So we're gonna go from this A to B. This there's A to B, and we're gonna try to find the length. So it'll be something like an integral between A to B of this particular thing. It's just a formula: 1 plus f prime of x squared and dx. I mean, that's just the formula. You just kind of want to remember that formula. All right, simple. Now, if we wanted to figure out the surface area, we can sort of think of it like this. Let's say we were going to rotate this around an axis, and you would see a mirror image down here. It would create a little design like this here, and you might even find it on the other side. In this particular situation, r is equal to f of x here, right? You can see this r around here, and we want to try to figure out the surface area of this thing. It's just a tube. There's no It's similar to what one of those shells would be, but it's now a little bit messed up. So we can use this 2 pi r. So we're trying to figure out the circumference again, and then integrate that across this area. Integrate across that length from A to B, which is the arc length over here. Just add that back in. 1 plus f prime x squared and dx. And so now we've sort of figured out, okay, from the length, arc length, we can actually create a surface area if we rotate this across an axis. And well, yeah, that's pretty cool. We also use integration for physics as well. So physics over here. Let's try to figure out the mass of, say, a line or some sort of a rod or some sort of a thing. And this basically has no like width or anything, but it has density across this. So the mass of this is going to be an integral from A to B, which is of course A to B here as usual, and px. This is going to be the density function, so px. Usually density is like a function or something like that. Integrated over dx. All right. Well, now we've got the mass of this wire. Let's say we wanted to make a thin disk out of this wire. Well, first we would have to wrap it around in a circle and be creating something like this. So here's going to be this wire that's wrapped around a circle like this. And let's say there's going to be like that's just one wire, but there's going to be instead a lot now. And they're going to form many rings here, just sort of create a sort of a area here. Okay, and this area has, it's just a disk, just a flat thing, but it's got a radius of r, and we want to try to figure out the mass really. We're starting from 0 going to r, and remember we started with wrapping this wire around in a circle, so we're technically going to start with the circumference, so 2 pi x here, 2 pi r, right, the circumference, and then we're going to use the density function to finish that off. Just multiply by the density, integrate it over from the entire radius right there, and dx. So that's going to be the mass for an area of a disk. It's kind of weird. And then we also have the classic work function. Work is that's just going to be equal to the integral from A to B of some kind of force, d of x. Cool. Some physics equation. Let's also calculate some moments. Moments. Imagine you had like a diving board right here, and you had a couple of blocks on here. So one block would be essentially would have a mass 1 and a x1, and the second one would have a mass 2 and x2. And in the middle here, you would have another point called the center of mass, because you'd have the center of all this stuff would be sort of balanced right there in the middle. And we want to use an integral to figure out how many of these, because if there was a lot of these, we could do something like this, that the moments is going to be equal to the sum from I is starting from 1 to some number n, and we'll switch these to blue numbers here now. They'll start to make sense. So we got 1, 2, and let's say we had a whole bunch, 3, 4, 5, whatever. We're going to just sum it up by m I, and then xi. Alright, and remember the center of mass thing, x with the bar on top, x bar, that's just going to be equal to the moments divided by the mass. Moment divided by all the masses, and summed up together. Now let's try the same thing for a set of thin plates. Here's some thin plates, starting like this, and we're going from this plate here to this plate here, and I'll try to make it quite symmetrical if I can, I suppose. We're also going to subtract some area down here just to make it kind of you could see how if I were to, I'll draw this in here, pretty much just like a symmetrical area around this center right here, and this area right here. Make this part red. Remember, we're sort of taking this out, but this little symmetric line here, this is where we find the centroid. The centroid is on the axis of symmetry. Okay. But anyway, if we were trying to find the mass of this, then we would first start with the density, and then we're just going to integrate from A to B. Here's A to B, and we're just going to subtract the two functions. So f of x minus gx. And there we go. Nice and easy. That one. If we're going to try to figure out the moments of this, well, we have to separate this out. We got to figure out the x moments and then the y moments. So mx. So remember that for x, we've kind of already figured it out. We can just figure out, you know, b minus a divided by 2. We'll figure out what the x coordinate is. But if you didn't have that automatically, if you didn't have any symmetry, you would have to use this formula right here. And you figure out a, b, and you can use 1/2, and then I have to do fx squared minus gx squared, and then the d of x here. All right, so we're just sort of deleting these two, putting this stuff together here. Let's do the same thing for my. It's really nothing to explain here. Just gotta write down these formulas. So a to b, and then this is a simpler one. So x and f of x minus g of x. Let's see similar themes across these. We're just subtracting these things from each other. Now the interesting thing about this is that we have x bar being equal to my divided by m. It's the total mass here, of course, and or the mass of this entire thing, and then the y bar is equal to mx divided by the mass. And I mean, that's how we could figure out what the thin plate is. It's just kind of a couple more simple formulas. Now we can try to derive some more volumes and surface areas of some strange shapes by using the theorem of Pappus. Where the hell Pappus is? Pretty smart. So let's say we have a weird shape, something like this. That it kind of looks like a cylinder, but I mean it's not, but it's kind of like a cylinder, right? So the idea is, in the cylinder you would use the radius to try to figure out the volume, right? Or the surface area. Start with surface area. Surface area would be the circumference, so 2 pi r, and then you would multiply that by well, the h. That's the height. I'll draw a little height in right here. So the h right there. And okay, cool. But let's say we were trying to figure out this one. In that case, we want to figure out what's the center r, that r bar, that would make this, like, basically turn this properly into like like for some reason that particular r makes it so that it's almost like perfectly a cylinder again, you know. We're just going to make that an r bar. And you could use that to figure out the you could use that here in the cylinder too, you just don't have to. But that's how you'd have to figure out like a slanted cylinder or something like that. This is the same thing for the volume, but volume in a little different way than you might expect, because let's make this a little bit thicker. This little line right here, I'm just going to make it thicker and thicker until it sort of forms this weird shape around it. And it's a 3D shape that's kind of really hollow in the middle, but it's pretty bulky on the edges here, and so that's going to have a very strange volume, because it's going to start with the 2 pi r again, r bar, but instead of being an h here on this side And I'll draw that bar again right over here. This is what we're looking at. This is why it's, instead of an H, it's an A, because now it's this type of volume. So it's not really like a, it's not a solid. This is kind of like a strange type of volume where it's like rounded. But these are referring to the thickness of this line right here. And that's the theorem of Pappus. It's a warped cylinder. All right, now let's remember some exponential rules real quick. We got x b is equal to x to the power of a plus b. And then we would have x to the power of b, that's equal to x a minus b. And if we had x to the a power of b, that's just equal to x ab. All right, that's just some exponential rules. And we can also study some exponential growth in blue and decay over here as well. So just a quick simple formula here as usual. We got a final value. You might be given, you're probably going to be given this initial value, and when time is equal to 0, the y over here, let's say I've got a little formula here. So it's going to be e to the power of plus or minus this constant k t. And it's minus if we're decaying, or plus if we're growing. And of course there's going to be a double or a half-life. And that particular time is just going to be equal to ln of 2 divided by k. Regardless of whether it's positive or negative k, it'll just give you positive time. And this is exponential growth and decay. Now we get to the fun stuff, the hyperbolic functions. Hyperbolic calculus. So that's going to be something like this. Let's say we have sinh. It's actually a little easier than the regular ones. Sinh is equal to the integral of cosh. All right, and over here we might look at cosh. It's important that we start cosh at 1 right here. 1. It's just a parabola. That's what cosh is. So cosh is equal to the integral of sinh. There's no negatives or anything. It's just cosh and sinh. There's integrals of each other, and they're probably derivatives of each other as well. Makes sense. And let's go over here to this side. This is going to be this for tanh. Tanh starts and ends -1 and +1. That's going to be equal to the integral. Remember, the tangent was had something to do with secant. This time it's secant squared, I guess. And over here we're going to be doing coth. So coth starts at 0 on that side and ends at 0 on this side, but that's going to be going straight to 0 there. But on this side, it's going to -1 and 1 over here. So this is going to be coth. That's going to be equal to integral. And on this side, they're all negatives. Oops. On this side, everything is negative, starting to become negatives. So we got negative, the negative integral of cosecant. Okay, that's what coth is. Now secant starts from negative infinity, or technically 0 is negative infinity over here. Anyway, it goes up to 1 right here. It's kind of like this little lump that just pops up there real quick. And that's sech. So sech is a little bit more complicated here. Remember that before it was sort of secant tangent is your derivative of sech. secant, but in this case it's secant tanh. So secant tanh. That's the first sech. And finally, we're going to be looking at cosech over here. Shazam. Bam. This time it goes from negative infinity to infinity and 0 and 0. This basically just goes wild. This is cosech, which is equal to the integral of negative integral. Let's not forget the negatives. Negative integral of cosech and then coth. So cosechant coth. All right. This is the integrals of hyperbolic functions. I guess a little bit more difficult, but at the same time it might make slight more sense if I start adding in the x's as well, because I kind of took them out. So if I have this thing right here, which is x squared plus 1, integral of 1 over x squared plus 1 that's actually equal to of arc sinh. All right, and I'm going to use a negative 1 up here in red. So remember, this is arc sinh, and then this is of x, because there's an x squared in there. Arc sinh of x. These are all things of x. It's not just h, it's actually of x. Yeah. Anyway, so the next one is going to be 1 over the square root of x squared minus 1. And that's going to be equal to cosh, negative 1. This is arcsine of cosh of x. Then we're going to have on the next line here, bam, 1 over 1 minus x squared. This is the easy one. This is going to either be tanh, an arctanh really, arctanh of x if the absolute value of x is less than 1, or it's going to be equal to coth of negative 1, arc coth of x if absolute value of x is greater than 1. And finally down here we could put a couple more. The integral of 1 over x times the square root of 1 minus x squared. This is going to be equal to, very important here at the bottom, they're all negatives, so negative sech, and this is arcsech, arcsechant, and this is the absolute value of x. Okay, and we would also have one for cosech, so that's going to be 1 over x, the square root of 1 plus x squared, and then this is equal to, again, negative cosech negative 1 here, arc cosech, and the absolute value of x. Whew. So that's a lot of things that we can do with the integral, and sometimes doing these integration methods can be a little bit complicated. So in the next video, we're actually going to look at some techniques that will make all these integrations a lot easier. Hopefully, if you like these videos, make sure to like and subscribe, and thanks for watching.